the points plus the waiting time. So time passes, and at some point of time, I waited a little bit, and I said, okay, if I would get here another request, then I might want to match it. But currently, I waited a little bit. I saw that there are no additional requests here, so I decided to match these two. So I draw it like that, because you wait. This is the time that you waited. And at that point of time, you decided to match them. And then you pay the cost, which is the distance between them. So we have two x's, the axis of distance and the axis of time. And you pay both of them. And then again, time passes. So actually, this match was a mistake because these 2 points are at the same location. They're people of the 2 level. So you should have waited a little bit and just match these two, but you did not. So you get more points, and then you have to decide online how to match. You get one more request, and then you decide to match these two. This waited a little bit, but this waited quite a bit until it is matched, and so forth. So so this is in general the picture of what's going on. Note again, this is the metric space, and this is time. Okay. Michal, do you have the?
I already gave it to the next speaker.
Okay.
So what is just the difference between level plus the waiting time?
So it's written here. We have a metric space. Requests arrive over time at the metric space, and we need eventually to make a perfect matching between the requests. And the cost has 2 ingredients. One is the connection cost, which is only the vertical cost, and one is the delay. And the delay is a horizontal cost. And you look at the sum. Of course, there is no big difference between sum and max, but okay. Now it will be a bit easier for me. Okay, so the goal is to minimize. You don't want to pay neither lot in the time, not in the cost. Okay, motivation 2. This one version of a problem. The other problem is many people know about it. It's the Uber Lyft problem. So again, you have customers which arrive at a certain times and certain locations, and they want to be matched to drivers. Drivers also arrive at certain time locations. Why? I mean, it's clear why customers arrive at certain time locations, because they want a service. And drivers also typically drop a previous customer, and then they are available for service. And the action is that you need to match the customer to driver. That's obvious. Each customer needs one driver. And the goal is, again, to minimize 2 ingredients One is a distance. Like if you are in San Francisco, you don't want to match someone in New York. That's obvious for using the Uber. But even if you are in north side, the north town, you don't want to match someone in the south, and so forth. And of course, you need to delay. If the only one is very far away, or there are few that are far away, you need at some point of time to match them, because you don't want to both drive, especially the customers, but as well the drivers, to wait a lot until they are matched. So this is another version of a problem. And again, if I explain it in mathematical terms, I have a metric space, which is here. I have the time, which is here. Over time, I get requests, but now I have 2 types of requests. This is supposed to be red, and this is blue. And I get it over time. I cannot, these are pretty close, but I cannot match them because they are both customers, or they are both drivers. And then at some point of time, I mean, I could match them immediately, but I was not sure if I should match them immediately. I waited a little bit and then decided to match them. And again, it was a mistake because I should have matched it like that. And again, I'm waiting. I get more requests. And again, I decide to match as time passes. And I can decide to match at any point. I mean, I don't need to do it immediately. I can do it over time. But I'm paying the delay. So I could postpone it as much as I want, but there is a cost to that.
So here the real picture should be 3-dimensional, right? Because the magic is really Euclidean or something.
Yeah, I mean, here it's not a line. Here it's a metric space. It's a metric space. I mean, the distance is not really a line. I mean, you should put here a full graph, but I'm limited in ability of hashish way to make pictures. Yeah, and yeah, I didn't do it. So and so forth. So I guess, and I think it's quite clear. I hope the two versions of a problem are clear, and neither one of them is a special case of the other. There are two versions, very similar, but still somewhat different. Okay, and so forth. So I hope that the two questions are clear. So I'll start with the, okay, I start with the first. Okay, so first of all, just to recall that the algorithm is called alpha competitive if the cost of the algorithm at most alpha times is the cost of the adversary that knows the whole sequence in advance and has unlimited amount of computation. So Yuval Mekshai-Kuten and Roger Wattenhofer suggested this problem and look at the homogeneous case. Homogeneous case is we have only one type of players, such as in chess. And they show the log square n plus log delta in a general matrix space. It's a randomized algorithm. And n is the number of points in the matrix space. And delta, not the number of requests. The number of requests could be unlimited. You could have as many requests as you want. The matrix space is limited to have n points. And delta plus log delta, where delta is the aspect ratio of the matrix space. The longest distance divided by the shortest distance. And our result, so we ask ourselves, can you get a competitive algorithm which is independent of delta? Do you really need to get dependence on the aspect ratio? And the answer is not. We give log n competitive algorithm, which means, first of all, we got rid of this. And the log square n is also not required. It's only log n competitive. And the second question actually, is it the best? Can you even get maybe a constant competitive algorithm? Maybe it doesn't depend at all at n. But the answer is negative. We show a lower bound that with a matrix space of n points, you actually need log n over log n. The competitive ratio is at least log n over log n. And this is even for simple matrix space. Simple matrix space means that it's a line. There are simpler matrices, like if the matrix space is a uniform one, then actually our result, I'll mention it later, actually you can get a constant. But for the line, the competitive ratio is at least log n divided by log n.
Even if it's some dependence on delta?
So even for, of course, you can replace, typically people don't want to get things which are dependent on delta, but I'll mention the lower bound, it's even n equally spaced points on the line. Even for that, you get a lower bound of log n divided by log n. Okay, so the first thing, so I'm now going to describe the algorithm. For that, I first of all want to remind you about embedding. Instead of looking at a general matrix space, there is a simpler reduction that shows that you can only look at trees, actually distribution on the trees, and lose a factor of log n, or more precisely, an embedding of one matrix space to another. First of all, if you want to embed d to d prime, you only need to increase the distances. You cannot decrease them. However, you want not to increase this by too much, by a factor of mu. So mu is the distortion of the embedding. And it's hard to get, it's impossible to get useful deterministic embedding. So therefore, you look over distribution over embeddings. And here, and the mu is actually the expectation. So the stretching of the distance is in expectation. But still, it's fine. So you can get a good embedding. And there is a trivial, actually almost a trivial fact, that if you have an embedding in which the distortion is mu, and you can get alpha competitive on matrix space which you embedded into, then you lose only a mu factor, which is the distortion. And a well-known result of FRT shows, a previous result of Yair Bartal, is that you can actually get, if you are ready to lose the log n in the distortion, then it's enough. You can embed it with what's called HST. Yeah, trees. In particular, it's trees. It's even more structured trees, hierarchy trees, but even trees will be enough for us. So from now on, I will only consider more or less trees. Actually, we need to be a little bit more precise. It's not so important to understand it, but whoever wants to know it more exactly, we actually define an algorithm which is beta-gamma competitive. It will be beta competitive in the connection cost and gamma competitive in the delay. So the algorithm will be beta-gamma competitive. Such an algorithm is in particular the maximum between beta and gamma competitive. And the advantage of this definition is when we lose in the embedding, we lose only in the beta, we don't lose in the gamma. And this is slightly more refined, but it doesn't matter if you don't use refinement, and instead of log n, you will get log square n. Of course, we want to get log n, so we need to use this refinement. And in particular, our main result is a deterministic algorithm, which is constant competitive for trees of height h, which is constant competitive in terms of the connection cost, and h competitive in terms of the delay. So now, since it's true, I mean, usually the tree that you embed can have a large height. The height could be log n, but there is a result of Bourbinder et al. That shows that actually you can only think about trees of height log n, so you lose here a factor. So h is at most log n. And now, since in the connection we get actually a constant competitive, and the distortion is log n, so you lose only here a factor of log n. So we get log n, and then you get a log n competitive. So from now on, what I only need to show you is an algorithm for trees, which is constant competitive in terms of the connection cost, the distances, and h competitive, where h is the height of the tree, in terms of the delay. So this is what needs to be shown. Okay? So now I'm going to describe the algorithm by picture, and then I'll show it formally. So, okay, so here's the picture. So this is the tree. Again, it's not HST, whoever know, most people know, but it's for arbitrary tree, and it has a height h. All the points of the metric space are the leaves of the tree. I mean, this is without loss of generality. And okay, the colors are not great. And each point in the tree has a counter. And you have actually four types of counters. One, okay, let me explain it. Okay, let's say that at time 0 you got 4 requests. Here, 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 and here, and here. So now for each point, each point in the tree is either odd or even. It's odd if the number of requests in its subtree is odd, and it's even otherwise. So for example, the colors are not clear. Here it's odd because it has 1, and here it's also 1. But this, for example, is even because it has 2 requests in its subtree, and so forth. So what's supposed to be color? Yeah, you don't see the colors very well, but you can see still the difference between the yellow and the other color, which I'm not sure what it is in this screen. So there are the odd and even. And now you have each such a point as a counter. It's increasing over time. It's increasing at rate 1 if it is odd. If it's even, then it doesn't increase. So this counter, the 4 yellow counters, does not increase because they have even number of requests inside. So the idea is that you're supposed to match the point in the metric space inside the tree by themselves because you have even number of requests. So you don't need actually to go up. And of course, the odd ones, you need to go up, so the counter will be increased. So at the first level, all the counters which are odd increase by 1. So you have 1, 1, 1, and 1. And since this distance is 1, so actually the counter becoming equal to the distance to its parent, so therefore you already paid in some sense to the distance to your parent. Therefore, at that time you buy this edge because you already paid for it. So you buy this edge, and this counter is becoming saturated. What does it mean saturated? It cannot increase anymore because it has already bought the edge. Okay, and all the other counters are still 1 and are not yet ready to pay for the edge upwards. Now one more time passes, so all the counters which are odd becoming 2. So again, this one becoming 2 and actually can buy this edge and so forth, and actually they becoming saturated. And one more time passes, this has become 3, and this is becoming saturated now, and both. So now we bought this edge, and this edge. Since we already bought them, virtually bought them in some sense, now we actually match this request to this request. Once we bought a full path between 2 points, then we actually match the 2 requests, and since its match is actually disappear. I mean, the requests disappear, and all the counters between the 2 are reset to 0. Okay, now one more time passes, so this is becoming 4. This is becoming 4, so these are 2 are both, and this is becoming 5. Now, if you will wait one more time, so you will see, I mean, we have almost here, we can match these 2 because the counter is 5, the distance is 6. So in one more unit, this will be both, and then we can match the 2. However, at time 5, we got 2 more requests. We got a request here and a request here, and therefore this counter now become even. Once it's become even, then it stops increasing anymore, and so forth. And this is the algorithm. So and you continue like that. Okay, so this is how it works. Now, if I want to define it in more mathematical terms, so I'll describe it if it was not clear from the picture. Then again, each vertex is either odd or even. It's odd if in its subtree there are a number of unmatched requests, which is odd. Otherwise, it's even. And at the beginning, we didn't buy any edge in the tree. Now, when you get a new request, then you update odd and even. Everything from that node to the root actually changed its polarity. If it was even, it becomes odd. If it was odd, it's becoming even. And then each counter is increasing at a linear rate if it is odd and unsaturated. If it's saturated, it should not increase anymore because it was already bought. And if it's odd, then it's increasing. And once it's becoming saturated, means that the counter becomes equal to the distance between this node to its parent, then you actually buy this edge, and this edge, you add it to this edge. So it's becoming part of the edge which are bought. And then if we bought a full path between 2 requests, then we actually connect them. This is a time that we really do something in reality. All the rest are only virtual in some sense. And then we reset all counters and of course update odd and even because we match 2 points. Okay, so this is the whole description of the algorithm.
Why do you know the tree? I mean, you need to know the tree in advance, right?
Yeah, but this is typically the embedding. You are given the metric space in advance, so you know it's a distribution over a trees. So this is kind of standard. You pick one at random, and you work on this random. So the algorithm is, the algorithm that we describe is deterministic on the trees, but the embedding is randomized, which means this is a standard techniques in embedding, that you choose one at random, and you work on this thing, on one random tree.
It's not the most general adversary. I mean,
it's not the most general?
adversary model, right?
No, typically, okay, when online algorithms started, people looked at different types of adversaries, but after a couple of years, it converges only to the oblivious adversary, because the other ones are not strong enough, and they are close to the deterministic algorithms. So people from the last 20 years, more or less, only consider, I mean, this is a little bit of an exaggeration, but people only consider almost all oblivious adversary. Okay. So it's a little bit too late to give you the full proof. The proof is quite simple, actually, but it still requires some work, and I don't have so much time. I'll just give the highlight of it. So the first observation is that the number of actually the number of requests is bounded by at most twice the number of odd unsaturated vertices. Let me explain what does it mean. Note what is the odd unsaturated vertex. Odd unsaturated vertex is vertex that it's going to increase. The counter is going to increase. Because if it's odd, it's going to increase. If it's even, if it's not. If it's saturated, then it reaches its maximum, so it's not going to increase. So then I want to bound the number of requests as a function of the number of odd unsaturated vertices, because their counter is increases, so I can charge the number of requests to these counters. And the reason for that is it's quite simple, but I'm not going to describe it. I can actually look at all pending requests, all requests which were unserved, and match them in a disjoint way. There is always a way to match them in this disjoint way. And it's on the path between two requests, one of the counters must be, all of them are odd. It's easy to see that all of them are odd, even if there are other matching going all around. And one of them must be unsaturated, because if all of them are saturated, then we already match them. So this is one thing. And yeah, I think I'll skip it. Now we actually define counters which are not reset. And this is like important, but I'm not going to have time to describe it. And actually the main lemma, this is one of the two main lemmas, is that the delay can be bounded by the counters. The idea is as follows: as long as there are requests which are pending, which are not served yet, one of the counters for each such request is increasing. Therefore, if I sum up all the counters, they bounded me the algorithm delay cost. Moreover, the second one is it's obvious that the connection cost is actually bounded also by the counters. So the idea of the proof is to bound the online algorithm, the cost of the online algorithm, by the counters. This is easy because only once the counter becoming saturated, becoming larger than the edge to its parent, only at that time I actually bought an edge and I'm going to use it. So eventually, if I sum it up, the cost of the algorithm is bounded by 3 times the sum of the counters. And now the main lemma, which is the second lemma, which I'm not going to describe, is why the adversary needs to pay this amount. So the invariant is a bit tricky. It's a bit tricky. I'm not going to explain it. I'm just going to describe it. The invariant is a bit tricky. I look at each vertex and I look at all the counters in its subtree. And I want to bound the adversary cost on this edge plus the adversary delay on all the subtree, not on a specific point, but I want it on all subtree, on the whole subtree below this point. And in some proof, which is not very complicated, if I had 5 more minutes, I could explain it. And if it was not 2:30, if it was 11 in the morning, it would be a little bit better. But I mean, it requires some concentration. And you can actually show that the adversary can also be bounded by this function, by these counters. However, for the adversary, we need to we don't know that specific cost on a specific edge and a specific counter is large. We know that the cost of the connection cost plus all the counters below together are high enough. And therefore, if we do the right computation, each counter is actually counted. The number of times that it's counted is the height of the tree. Therefore, we lose a factor of h, and I'm not going to describe it. So this is the idea. Okay, let me just sketch. So this was for the homogeneous version, in which requests are of the same type. If we have 2 types of requests, I only describe the algorithm, it's very simple, then the algorithm is a bit different. So again, we have the same tree, we have the same counters, but now we have blue request and red request. It's not at each intermediate point, it's not the question if it's odd or even, it's the question if it has more red or more blue. It's a question of between the how much the discrepancy between the red and the blue. And the the counter is increasing proportional to the discrepancy. So a little bit more complicated because the rate now is not 1. It's the difference between red and blue, and it's important if there are more red than blue or more blue than red. And the algorithm is the same structure. And again, once you buy an edge, you buy an edge, but you can buy it as edge as blue or red, and so forth. And once you have a path, you connect it. That's the idea of the algorithm. And it's a bit, it's the same flavor, a little bit more tricky. And again, also for the two-sided version, we can get a log-n competitive algorithm. The algorithm, as I said, is a little bit harder, but gets eventually the same competitive. OK, the lower bound is, I'm not going to describe it, just the idea. Again, we have endpoints equally spaced. And time passes, we have many, many phases. And in each phase, we have less and less points. And we have two options, and the algorithm doesn't know which option you will get, and so forth. And I don't have time, so this is the idea. Very simple, but tricky. And as I said, two-sided. The problem is that for the lower bound, actually, although the two-sided version, which it's a Lyft Uber version, you have red and blue, are actually, it seems harder, the algorithm is harder because it's not a question of even or odd, it's a weighted version. It looks like the algorithm is a weighted version of the homogeneous case. Our lower bound is worse. This is because our disability to prove lower bounds. The lower bound is actually, the lower bound for the homogeneous case is log n over log n, and for the two colors, which is supposed to be harder, is actually weaker. It's square root of log n over log n.
The lower bounds are also for randomized algorithms?
Yes. Mm-hmm. So I'm ready to summarize, to be on time. So summary, again, we look at two versions. The homogeneous problem, a game platform, which you need to match pairs of people, and the two-sided customers to drivers, and so forth. For both problems, we got log n. It's randomized. Again, for a tree, it's deterministic, but because of the embedding, it's randomized. Lower bound, as I said here, it's almost tight up to a log n factor of the homogeneous. This seems harder, at least the algorithm is harder, but the lower bound is weaker. So it's this type of anomaly. And future work, OK, we show log n competitive. Our algorithms are randomized because of the embedding. It's interesting to know something about deterministic algorithms. Either you can get maybe polylog algorithm deterministically, or show a lower bound. The best algorithm that we have is actually linear. It follows from the proof that I described, but we don't know sublinear algorithm for the deterministic one. Another problem is other delay functions. For example, if you are waiting, if you wait too much, then you're becoming nervous. So customers are not, the function is not linear. So if you wait a lot, you're becoming more nervous. So you might want to pay, let's say, quadratic cost. So if you wait some amount, you pay the quadratic of it. So people are impatient. You don't want them to wait too much. It's not clear how to deal with other delay functions. Find other problems. As I described it, most online algorithms deals either with cost or with time, and this problem combines both cost and delay. And that's it. Mm-hmm. Yes?
Did you consider a problem in which, for the two-sided problem, drivers have capacity? So it's not pairs that you need to create, but drivers have capacity, and there is also a global objective of minimizing the number of cars.
Yes, so actually you can look at games that have 3 or 4 players, like Bridge. And in the two cases, it's like capacity.
In which you must form groups of 4.
Uh-huh. Here you
select, you have a capacity, the maximum number of passengers.
OK, this is the next action we're going to work on. Yeah, no, we haven't considered it, but it's a really good version. Yeah. Mm-hmm. But here we only, then you need to maybe model where is the target. I mean, here we only model that you need to come to the customer. We don't care where he's going to. The driver is only coming to the customers. He needs to go anywhere. And then you have to make it more complicated. Mm-hmm. Yes?
So you consider here a worst case.
Yeah.
So Uber and these kind of things are not really worst case. They are more, they have kind of a distribution over the inputs, so like a stochastic arrival thing. This is definitely...
It's definitely a good direction.
Good, right? And another thing about the... so this is a matching. What about if instead of matching like a single edge, I would consider a different kind of offline input in which, I don't know, it's a graph and I want to have routes. Instead of matching them with a single edge, like have a route.
Yeah, it's a good version. We have I mean, there are very different versions. I mean, this is a good, I mean, this is what I said in the lab. Find other interesting problem with cost and delays. Mm-hmm. It's a little bit tricky because you need that the optimal algorithm will also get something from delaying things. Because if optimal does not gain any, in this problem of matching, optimal also gains something because he still needs, if he gets a request at the near points, he still needs to wait. The optimum also wait. If you have a version in which the optimum does not need to wait, then there is no way to solve it. So you have to define it appropriately. Okay, I don't want to get any more take time of the others.